Hello everyone, my name is Kawa Yip and I'm a grad student at USC. So this is my APS March meeting talk. The topic is reverse quantum annealing with dissipation. This is a joint work with people all around the globe, and for more information, please refer to our paper online. The motivation of this project is to explain the reason behind the results, two different results of two previous studies. One previous study suggests that reverse annealing adversely affects the performance for the PSP model in a closed system setting, while a second study shows that reverse annealing actually gives enhancements for random spin glass instances in D-wave experiments. So we would like to see if the open system effect in experiment is the mechanism that gives rise to this enhancement. So as an overview, reverse annealing can be separated into two formalisms. One is a diabatic reverse annealing, ARA, where S starts from 0 and goes to 1. The second is iterative reverse annealing, IRA, where S starts from 1, goes to a particular inversion point, S inverse, and goes back to 1 again. And S inverse is smaller than 1. And this formalism, or this protocol, is used in D-wave, and also the one that we focus on in this project. So to dive deeper, in IRA, the annealing Hamiltonian is actually the same as for conventional forward annealing. So we have the transverse field, we have the problem Hamiltonian and the A and B term. But the difference is for iterative reverse annealing inside the A and B function, we start with S equal to 1. And in the reverse part, we decrease S till an inversion point S inverse. And in the forward part, we increase S back to S equal to 1 again and do the measurement. So, and also we can start a new iteration from the bit string obtained from the measurement of the measurement outcomes. As an example, we have the typical A and B schedule in the wave. But the difference is in iterative reverse annealing, S starts from 1, goes to a particular inversion point S inverse. So let's say 0.6 in the subplot B and goes back to 1 again. So this looks like an inverted triangle, while for forward annealing, standard annealing, it is a monotonic increasing straight line. So as mentioned before, one previous study says that shows that the iterative reverse annealing gives a negative result for in a closed system setting. So we would like to explain why that is, and to compare the reverse annealing to the one that is in an open system setting. So as an intuition, for closed system, if we start the reverse annealing, so from let's say the first excited state, we are basically solving the Schrodinger equation, and that means it always stays inside that eigenstates, a time-dependent instantaneous eigenstate, unless there is a significant degree of diabatic transition. But if the gap is big, then we do not observe a large population transfer to the ground state. But for open system, while we are doing reverse annealing, there can be relaxation that is induced by the environment, and that relaxation can take some portion of the population to the instantaneous ground state, and they can be carried on by the APS process to the correct solution state at S equal to 1. So to test our iteration, we would like to simulate some dynamics for the particular model called the PSP model. So the PSP model has the following problem Hamiltonian. And even though odd P leads to different properties of this Hamiltonian, like degeneracies of ground state, of phase transitions, and we focus on the case of P equal to 3. P-spin Hamiltonian is good for annealing in the sense that if one constructs the time-dependent annealing Hamiltonian from the P-spin Hamiltonian by appending it to the transverse field, the annealing Hamiltonian commutes with the spin operator S squared. So that means at all times, the Hilbert space can be expressed as a direct sum of spin sector subspaces. So let's say if one initializes the state inside the maximum spin subspaces, there is a simultaneous eigenstate of S squared and the annealing Hamiltonian now. So that means the dynamics always stays inside the maximum spin subspace. Also, I would like to introduce a notion called magnetization. That means how excited the eigenstate of the problem Hamiltonian is. So let's look at the results of unitary dynamics, closed system dynamics. We focus on n equal 20 qubits. As you can see from on this plot, it shows the success probability versus S inversion. By success probability, I mean how likely we will find the solution state at the end of the whole reverse annealing protocol. We can also see a lines of 4 different colors. For the red color, it means it will start from m0 equal to 0.9, the first success state. The result is reasonable for the red line. That means the maximum success probability can be as high as 0.8, while for the results of other lines, the results the success probability are generally low. So at this point, I would like to define 3 success metrics for to assess whether the reverse annealing is good or bad. So the first one is the maximum success probability achievable, which is around 0.8 for the red line. The second is how small the inversion point needed to achieve the maximum success probability. So here it's around 0.1, which is smaller than the minimum gap indicated by the dashed vertical line. So we need to reverse to anneal a lot less than the minimum gap point. And the third is how it performs with different initial states. So only the red line gives a good result, while the other initial states give a bad result. So reverse annealing in a closed system fail according to this matrix. So we would like to turn on the interaction with the environment in an open system to see if it improves. So, so the assumption is that the system is weakly coupled to the environment, and that means we can use a diabatic master equation to solve the dynamics of the system. The specific form of the Lagrange operators in the master equation depend on the system Barth coupling. So we studied 2 system Barth couplings, the collective and the independent. In collective system Barth coupling, in the case of dephasing, it is the famous collective dephasing model assuming a lot of literature. This system Barth coupling model is good for us in the sense that the Lagrange operator derived actually commutes also with the annealing Hamiltonian. So that means if one starts inside a particular spin sector subspace, it always stays there. That is good for simulation in the sense that we don't need to simulate the system in the whole Hilbert space. And also one can find the DFS, the coherence-free subspace, if one wants to. For independent system Barth coupling, we also have the Lagrange operators, but there are many more. And also the spin symmetry is broken for the assumption. So the simulation is a lot more expensive there. So let's look at the collective coupling model. To do the simulation, we actually unravel the adiabatic master equation into quantum trajectories, and that can take the parallel computing into our advantage and speed up the process. So the simulation results as follow. So we also have the 2 similar plots as in closed system, but right here we can see that for lines of all colors, the maximum success probability can be as high as 0.9, which is a significant improvement over the closed system results. And also, the S inversion point at this maximum success probability is actually near the minimum gap point. So we don't have to reverse anneal a lot to the way back to the minimum gap point. We just have to reverse anneal at that point to that point. And so in system collective coupling model, the high success probability of inversion points at around the minimum gap point and can achieve high success probability for all initial states. How about independent coupling? The independent coupling is a little bit worse than collective coupling in the sense that the success probability is not as high as the collective coupling. Also, the maximum success probability decreases more rapidly as system size increases. So that is worse in the scaling sense too. But nevertheless, this independent system of coupling still gives better results than in the closed system. At last, we would like to apply pausing to the reverse annealing. By that, we mean applying a pause with a particular duration TP as the S inversion point. TP, the order of TP is around the same as the total anneal time. We can see the results of pausing here. The results are the best compared to the open system simulation without pausing and also with closed system simulation. So we can look at it here. The maximum success probability improves to around 1, and that means 100%. And also, the S inversion required to achieve that 1 success probability is actually larger than the minimum gap points. So we don't need to reverse anneal back to the minimum gap points too. And also it happens for lights of all colors. Better still, if we do apply pausing, even if we assume independent system buff coupling, the maximum success probability is actually around the same or comparable to the collective system buff coupling. So the result is now indifferent to whether we assume independent or collective system buff coupling. So pausing leads to even higher success probabilities, and that high success probability can occur at large inversion points. And also there exists a range of upon 2 of optimal pausing points. So right here, there's a range of regions that we can search for. And also the results are less dependent now on the system buff coupling if we apply pausing. In conclusion, our study suggests that reverse annealing performs better in an open system than in a closed system because of dissipation. And also since closed system fails in closed system reverse annealing fails, while open system reverse annealing succeeds, thermal relaxation is the mechanism that is responsible for the success. Whether this can also lead to quantum speedups is an interesting question. Further directions includes implementing this reverse annealing on actual annealers, and also of piece middle on actual annealers, and also whether thermal relaxation can also benefit the other formalism of reverse annealing, the adiabatic reverse annealing too. Thank you very much.